Hello everyone, and welcome to the M2L31 Level 1 training course. In this session, I'm going to walk you through one of the peripherals inside the low power domain of the M2L31 series, the Low Power SPI. Inside the low power digital logic, we have several low power peripherals, including low power PDMA, low power GPIO, low power ADC, low power I2C, low power SPI, low power UART, low power timer, and tick timer. All of these modules can continue operating even when the CPU goes into sleep mode, and they can also serve as wake-up sources for the system. The low power domain is made up of the low power digital logic and the low power SRAM, and its clock can keep running independently from the core power domain. This architecture is ideal for handling periodic tasks or event-triggered tasks while the system is in sleep or standby mode. As highlighted in the diagram, the available clock sources include the 1 to 8 MHz MIRC and the 12 MHz HIRC. Now, let's move on to the Low Power SPI, also known as LPSPI. This module allows the MCU to maintain SPI master communication capability even while staying in sleep mode, and it can work together with modules like LP timer and low power PDMA. A very typical use case is periodically reading data from a low power sensor. We also provide an application note and example code using the M2L31 series together with a low power pressure sensor. For more details, you can check out the Low Power SPI example video in the training playlist. Here, I'd like to walk you through the differences between the regular SPI and the Low Power SPI in the M2L31 series. In the middle of the table, you can see that the regular SPI modules belong to the core power domain, and the M2L31 series provides up to 4 of them. These SPI can also switch to I2S mode, so they work well for audio-related applications, such as interfacing with audio codecs. On the right side of the table, you'll find the Low Power SPI. This module is placed in the low power domain, and its main purpose is to keep basic SPI communication available even when the system enters a low power mode, for example, when you need to continuously read data from a sensor. Low Power SPI also supports auto operation mode, which allows it to handle the transfer automatically while the MCU is asleep, achieving even lower power consumption. Another difference is the direct memory access support. The regular SPI uses the standard PDMA, while the Low Power SPI works with the Low Power PDMA instead. Now let's take a look at the pin functions of the Low Power SPI. Low Power SPI supports full duplex, synchronous serial communication in both master and slave modes, and it basically uses 4 signal lines: SS, CLK, MOSI, and MISO. Let's start with SS, also known as slave select or chip select. The SS pin is used to choose which slave you want to communicate with, and it's typically active low. In master mode, SS is an output. When the master pulls SS low, it indicates I'm going to communicate with this slave, and pulling it high ends the communication. In slave mode, SS becomes an input. The slave only starts sending or receiving data when the master pulls SS low. If your system has multiple slaves, they all share the CLK, MOSI, and MISO lines. But each slave has its own SS pin, and the master controls each SS individually. Next is CLK, the serial clock. CLK defines the timing of the data transfer. In master mode, the master outputs CLK and sets the communication frequency. In slave mode, CLK is an input, and the slave uses it to latch or shift data. Then we have MOSI, which stands for Master Out, Slave In. In master mode, MOSI is an output, and sends data on the selected clock edge. In slave mode, MOSI becomes an input and samples the data according to the clock. Finally, MISO, which is master in, slave out. In master mode, MISO is an input that receives the data sent by the slave. In slave mode, MISO is an output, but it only drives the line when its own SS is pulled low, meaning the master has selected that particular slave. And that covers the 4 essential signal lines used by SPI. Here, let's walk through how data is transferred in master mode, and I'll focus on the timing signals and what's happening at each step. Since the low power SPI is full duplex, the master can send data to the slave and receive data from the slave at the same time under the same clock. So let me explain the whole timing sequence step by step. First, the master selects the slave. The master pulls the SS line from high to low, basically telling the slave, "I'm about to start talking to you." This marks the beginning of the whole transmission. Next, the master starts generating the clock. Once CLK starts toggling, the transfer window is open. And whether data is shifted or sampled on the rising edge or the falling edge depends on the TX NEG and RX NEG settings. Then, the master begins to send data on MOSI. Data is shifted out from the TX FIFO 1 bit at a time with every clock. The slave samples each bit based on the selected clock edge. In this example, the bit order goes from MSB to LSB, meaning the most significant bit is sent first. At the same time, the slave also returns data through MISO. The slave usually pushes data out on the opposite clock edge, and the master samples it on the configured receive edge. Again, it's 1 bit per clock, and by the end of the sequence, the master reconstructs a complete byte. Finally, the master finishes the transfer by releasing the SS line. When SS goes back high, it tells the slave, "We're done." The slave stops driving its output as soon as it detects SS is no longer active, and that completes the entire SPI transaction. So that's the full data transfer process of the low power SPI in master mode. Now let's take a look at how the slave select, or SS, works in an SPI transfer. The SS signal basically defines the active period of a transaction. Only when SS is in its active state do the clock and the data on MOSI or MISO count as valid. Once SS goes back to the inactive state, that means the transfer is finished. In the low power SPI of the M2L31 series, you can use 2 SS modes, active low and active high. In active low, which is the default, pulling SS low means active, and pulling it high means inactive. In active high, it's the opposite. SS high is active, and SS low is inactive. In the timing example shown here, as soon as SS enters the active region, the red box, the clock starts toggling according to the CLK POL configuration. Data then shifts out from the MSB down to the LSB. And once SS leaves the active region, shown in blue, the clock and all data lines return to their idle state, marking the end of that entire SPI transfer. Next, let's talk about the byte suspend mechanism. When your transfer length is configured as 32, 24, or 16 bits, the low power SPI allows you to insert a short suspend interval between each byte if needed. During this suspend period, the clock stays at its idle level, which is determined by the CLK POL setting. MOSI and MISO hold their values and do not shift new data. And once the suspend period ends, the SPI engine immediately continues with the next byte. In the M2L31 series low power SPI, the suspend duration can be adjusted from 0.5 to 15.5 SPI clock cycles. This gives you flexibility to meet different slave device timing requirements and helps improve overall compatibility. Now let's go over automatic slave selection. When Auto SS is set to 1 and used with PDMA, the hardware automatically controls the SS line, so the entire transfer can run completely automatically. If your application requires special SS timing, or you need to manually switch between multiple slaves, set Auto SS to 0 and control SS via software or GPIO instead. One important note: when using this feature, the SUSPITV value must be less than 3. Here's what happens with different SUSPITV settings. If SUSPITV is greater than or equal to 03 in hex, SS will toggle active-inactive between every transfer. If the SPI bus is still busy, SS can flip multiple times, which may cause the sensor to mistrigger or enter an incorrect state. What if SUSPITV is less than 03 in hex? SS stays active continuously and does not release between transfers. This is ideal for high-speed continuous transfers such as streaming or large data collection. Next, let's talk about how the TX and RX buffers work in the Low Power SPI. For the TX FIFO, writing data is straightforward. You just write your data into the TX register. The data first goes into the TX FIFO. Then the hardware shifts it out through the TX shift register, and finally, it's sent out through the MOSI pin. For example, you can preload 4 data entries into the FIFO, allowing continuous transmission without pauses or gaps. The RX FIFO works in the opposite direction. Data received on the MISO pin first enters the RX shift register. Once a full unit is ready, the hardware writes it into the RX FIFO. To read data, you simply read from the RX register, and you'll get the contents from the FIFO. During the entire transfer, both TX and RX can use DMA to move data automatically, so the CPU doesn't have to intervene constantly, reducing system load. Also, in LPSPI.c file, you'll find commonly used API along with ready-to-use examples. For more detailed guidance, you can check the sample code section and watch the Low Power SPI tutorial videos, which make the whole process much easier to understand. Here's an overview of the commonly used APIs in LPSPI.c file, along with ready-to-use example code. A more detailed explanation is available in the sample code section, and you can also refer to the Low Power SPI tutorial video for a full walkthrough of the example programs. Here's a look at the API operation flow for the Low Power SPI in LPSPI.c file, along with a simple explanation of the corresponding transfer timing. The overall concept is straightforward. You control the SS line in software, and during a single active period of SS, you can perform multiple consecutive SPI transfers. For each transfer, the basic steps are 1. Write data into the TX FIFO. 2. Poll the busy flag until the transfer completes. 3. Read the received data from the RX FIFO. And finally, pull SS high to end the transfer sequence. Now, let's go through the timing shown in the figure. Step 1. Pull SS low. This signals the start of an SPI transfer. All data shifting happens while SS is active. Step 2. Write the first byte 0x11 into the TX FIFO. Once written, the hardware begins shifting this data out. Step 3. Pull the busy flag. Wait until the byte is completely shifted out. Step 4. Read the first received byte from the RX FIFO. Since SPI is full duplex, while sending, the master simultaneously receives data from the slave. Steps 5 to 7 and 8 to 10 repeat the same process for the next bytes, which are 0x22 and 0x33, reading back their corresponding received values. Step 11. Pull SS high. This marks the end of the SPI transfer sequence. Let's talk about how the TX FIFO works. In the diagram, from left to right, we have 3 layers: TX buffer, then TX shift register, and finally TX skew buffer. We also have two status flags, TX empty and TX full, to show the FIFO state during transmission. Let's go through two examples. Example 1. Writing a single piece of data. At the start, TX empty is 1, which means the TX FIFO is empty. When software writes one piece of data, let's call it data 0, into the TX buffer, TX empty changes to 0 because now there's data in the FIFO. The hardware sees that the shift register is empty, so it immediately moves data 0 from the TX buffer into the shift register. The TX buffer is now empty again, so TX empty goes back to 1. Next, the hardware moves data 0 from the shift register into the TX skew buffer, arranges the bits in LSB first order, and waits for the clock to start shifting the data out. Example 2. Writing multiple pieces of data and checking TX full. We start again with TX empty equal 1. This time, software writes 3 pieces of data, data 0, data 1, data 2, into the TX FIFO. TX empty immediately goes to 0. The hardware takes data 0 from the FIFO and puts it into the shift register, starting the transmission. While the hardware is busy sending, the software writes 6 more pieces of data, data 3 through data 8, into the TX buffer. Because the FIFO has limited space, it eventually becomes full, and TX full equal 1, which means you can't write any more data. Now, the user has 2 options. First, wait until TX full goes back to 0, which means there's space in the FIFO, and then continue writing. Or, second, wait until TX empty equal 1, meaning all data has been sent before writing new data. Now let's go over how the RX FIFO works. On the receive side, the data flows like this: RX skew buffer, then RX shift register, and finally into the RX FIFO buffer. We'll use 2 examples to explain. Example 1. Normal receive flow. FIFO starts empty. At the beginning, RX empty equal 1, which means the RX FIFO is empty. External data comes in bit by bit following the clock, first filling the RX skew buffer. For a 32-bit transfer, bits are received in order from B0 to B31 in LSB first sequence. Once the skew buffer fills with 32 bits, the hardware moves this data into the RX shift register. Then the hardware pushes the content from the shift register into the RX FIFO buffer. As soon as the first piece of data reaches the FIFO, RX empty changes to 0. Each subsequent piece of data repeats the same process, and the FIFO continues to fill. Example 2. FIFO full condition, RX full and overflow. We start again with RX empty equal to 1. After the first piece of data, data 0, enters the FIFO, RX empty becomes 0. If more external data keeps coming in, but the software hasn't read the FIFO yet, the FIFO gradually fills up, for example, data 1 through data 8. When the FIFO is full, RX full equal 1. If new data continues to arrive, there's no space in the FIFO, so the hardware cannot write it in. The hardware will trigger the overflow flag, RX-OVIF equal to 1, to notify you that data has been lost. The FIFO itself does not overwrite existing data. Once the software reads data from the FIFO, say data 1, space becomes available, RX full returns to 0, and new data can continue moving from the shift register into the FIFO. Another thing about SPI full duplex need to be noticed is SPI is full duplex. So for every piece of data you send, you receive 1 piece at the same time. For example, if you send 4 pieces of data from the TX FIFO in a row, once the busy flag goes to 0, indicating all 4 pieces are sent, at the same time, the RX FIFO has accumulated 4 pieces of received data waiting to be read. So in your application, you need to pay attention to both TX FIFO and RX FIFO capacity and status to avoid RX overflow when TX is sending data. Now let's talk about Low Power SPI in the M2L31 series, specifically its auto operation mode in low power states. The idea behind this mode is that the low power SPI can perform pre-configured SPI transfers on its own, even when the MCU is in any of the NPD low power modes, without needing the CPU. At the same time, it can wake up the system using events if necessary. To make this happen, the first step is to set the trigger source. On the diagram, you can see the different trigger options in the red box on the left. Whenever one of these triggers meets its condition, it sends out an auto operation trigger. Once the auto operation circuit gets the trigger, it will automatically drive the low power SPI to carry out the transfers based on your preset parameters. If data needs to be moved during the transfer, the circuit will request the low power PDMA. So low power PDMA can automatically move data in and out of the SPI without CPU intervention. And if you've set up a wake-up event generator, the system can be woken up by events while the transfer is happening. That wraps up our training session on low power SPI. We also have demo videos showing practical examples of using low power SPI, which you can check out in the video list. Thank you for watching, and if you'd like to learn more, feel free to reach out to us anytime.